Hello everyone and welcome to this week's OpenGL 3D game tutorial, and this week is going to be the first of 3 tutorials about particle effects. This week we're going to be setting up some basic particle systems with the particles just being rendered as plain quads which always face the camera. Next time we're going to be texturing the particles, working on animating the particles and looking at different ways of dealing with transparency. And then the last of the 3 videos will be about instanced rendering, which will help us render the particles much more efficiently. To start this tutorial, you'll need to download the particles package from the description of this video and add it to your project's source folder, and then in Eclipse you can refresh your project to see the code. This package just contains an extremely basic shader program for the particles which really needs no explanation at all. It also contains a pretty much empty renderer class for rendering the particles, which we'll be working on in a bit, and finally it contains a completely empty particle class, and this is where we're going to start coding right now. So this class represents a single particle in the game, and the first thing we need to do is to decide on what attributes every single particle is going to have. So the first thing that every particle has is of course a position, a 3D position in the world. Secondly, every particle is going to have a velocity, and this describes the speed and direction that the particle is currently moving in. So the velocity is a 3D vector, and the direction of this vector shows which direction the particle is traveling in, and the length of this vector shows the speed that the particle is currently traveling at. The next thing that we need is a float which indicates how much this particle is affected by gravity. So a value of 1 here would mean that the particle is affected normally by gravity, and any values less than 1 would mean that the particle is a bit more floaty. Then we're going to have a life length float which just indicates how long this particle should stay alive for. Next we're going to have a rotation so that the particle can rotate, and we also are going to have a scale value so that we can change the size of the particles. And finally we just need one more float, and this represents the amount of time that the particle has been alive for, so I'm obviously just going to set that to 0 to start with. I'm then going to generate a constructor, and I'm going to use all of the attributes except for the elapsed time here, so that should give you a constructor looking something like this. Next up, I'm just going to generate a few getter methods for the particles. So I'm going to generate a getter method for the position, for the rotation, and for the scale values of the particle. I'm then going to create a new method, and this is going to be an update method which will be called every single frame to update the particle. And this method returns a boolean which indicates whether the particle is still alive or not. So if the particle has been alive longer than its life length, then this would return false, indicating that the particle should be removed from the scene. The first thing we're going to need in this method is a value for gravity, and we actually already have one in the player class right here. So I'm just going to set this to public so that I can access it from the particle class, but you might want to move this gravity value to a different class if you think it makes a bit more sense. So the first thing that we're going to do in this update method is to change the velocity of the particle based on that value of gravity. And this is also going to be affected by how much this particle is affected by gravity. And of course gravity is a change in velocity per second, so we need to multiply it by the number of seconds that have passed since the last time this method was called. The next thing that we're going to calculate is how much the particle's position should change this frame, and this is of course going to be based on the velocity, because the velocity indicates how much the position should change in 1 second. So if we multiply the velocity by the number of seconds that have passed since the last frame, then we find out how far the particle should move this frame, and then we can actually move the particle by increasing the particle's position by that change amount. The next thing we need to do is to increase the time that the particle has been alive for, so we're just going to increase the elapsed time variable here, and then we're just going to return whether the particle should still be alive or not, and we can find that out by checking if elapsed time is less than life length. So that's the particle class done, and we can now move on to the particle renderer class, which is in charge of rendering all of the particles in the scene. So in the constructor here, the first thing that we're going to do is we're going to create a quad, which is what we're going to use to render all of the particles. And I've already given you the vertices for this, so you simply have to load them up into a VAO so that we have a VAO of the quad, which all of the particles are going to use when they get rendered. We're then going to create a new shader program for the particles, and we're straight away going to start that, load up the projection matrix to it, and then we can stop it again. If we have a look at the render method now, that takes in a list of particles that need to be rendered. And the first thing that we need to do in here is to create the view matrix. And we can create a view matrix by calling the maths.createViewMatrix method, which takes in the camera. We then need to do a lot of the usual stuff to prepare for rendering, so we're going to call the prepare method. And in the prepare method, we're firstly going to start the shader to get that ready for rendering. And we're also going to call a load of OpenGL calls, which I've copied and pasted here. First, we're going to bind the quad's VAO, then we're going to enable alpha blending, and then this last call here is something that we haven't used before. I'm going to be talking about it a lot more next week, but it basically stops the particles from being rendered to the depth buffer, which is going to be important next week. Back in the render method, we're now prepared to render, so we can loop through all of these particles and render each one of them individually. So we're going to create a for loop here, and then for each particle, the first thing that we need to do before we render them is to create the model view matrix for each particle. And the model view matrix is the particle's transformation matrix multiplied by the view matrix of the scene. And usually we do this multiplication in the vertex shader, but this week we're going to do it in the Java code because it's going to make it easier for us to make sure that all the particles are facing the camera. So this method takes in the position, rotation and scale of the particle and also the view matrix of the scene. To start with, we're just going to begin creating the transformation matrix or model matrix for the particle in the same way that we always have. So we create a new matrix and apply the translation to the matrix with the particle's position. However, we now need to do something a little bit different. What we want to do with the particles is to ensure that they're always facing the camera so that you never see behind a particle or see a particle side on. If we were to render the quads without a model matrix or a view matrix, then they would always be facing in the Z direction directly out of the screen, because that's how I set up the vertices for the quad. Just like for the first few tutorials or in the GUI tutorials, we were rendering quads then with very similar vertices to what we're using here, and those quads were always facing in the correct direction because we weren't applying any rotation to them. However, when we render objects in the 3D world, we have to transform their vertices using a model matrix and a view matrix, as I explained back in tutorial 8, and by doing this the camera is able to look around the world and see objects from different angles. Here you can see some particles being rendered in the 3D world, and the particles obviously aren't always facing in the correct direction because the view matrix is applying a rotation to the quads to simulate the camera moving around. We need to make sure that no rotation is ever applied to the quads, but we still want to use a model and view matrix so that the particles can be part of the 3D world and still move relative to the camera. The way to do this is to make sure that when we multiply the view matrix with the model matrix, that the resulting matrix, the model view matrix, contains no rotation at all, so when it's applied to the quad it doesn't rotate it away from its original orientation. Now, to understand how to do this, we need to know a little bit about matrix maths. So this is what a 4x4 matrix looks like, and the rotation is stored in the top left 3x3 part of the matrix. If there's no rotation, then that top left 3x3 part will look like this. So that's what we need the top left part of the model view matrix to look like. So when the view matrix is multiplied with the model matrix, the result needs to have no rotation. So we're going to choose the rotation part of the model matrix so that when it gets multiplied with the view matrix, the result is a matrix like this without any rotation. And I'm not going to go into the maths behind this, but to do this we need the rotation part of the model matrix to be the transpose of the rotation part of the view matrix. And to transpose a matrix, you basically just swap around the rows and the columns. So if we have a view matrix like this, then we make the rotation part of the model matrix the transpose of the view matrix rotation part by swapping around the columns and the rows. And then when multiplied together, they'll create a matrix like this, which has no rotation. If you want to know more about matrix maths and multiplication to be able to understand this a bit better, then you can follow the link in the description to a web page which explains the basics of matrix maths. So let's now implement that in the code, and we're going to do that by individually setting each of the elements in that 3x3 rotation part of the model matrix. And I've probably put this in the code somewhere commented out for you so that you can just copy and paste it, because it's a bit annoying to have to type out each of those lines there. So now that the particles are all facing the camera, we can actually rotate them along the camera's Z-axis. so they can be rotated but still facing the camera. And we can do that by calling the matrix rotate method, and that takes in the rotation in radians and the axis along which we want to rotate, which is the z-axis, and we're going to be using the rotation to rotate the model matrix here. And we also are going to need to cast that to a float, and we also want to scale the model matrix. We want to be able to scale our particles, so we're going to scale uniformly along the 3 axes. So we're going to use the scale value on all 3 axes there, and we're going to be scaling the model matrix. And now we can do the same multiplication which we've always done in the vertex shaders, and that is to multiply the view matrix with the transformation matrix, or the model matrix. So here we're going to create the model view matrix by multiplying the view matrix of the scene with the particles model matrix. And once we've created that new model view matrix, we can load it up into the shader, and we need to call this method for every single particle before it gets rendered. So we call the update model view matrix method. That takes in the particle's position, the particle's rotation, the particle's scale, and also the view matrix of the scene. So now that we've prepared for rendering, we've updated the model view matrix for the particle that we're currently rendering, and now we can actually render that quad to the screen, and we're going to use GL draw arrays. We're going to need to use GL triangle strip here like we did when we were rendering GUIs, and obviously the number of vertices that we want to render we can get by doing quad.getVertexCount. So after the for loop, we need to call the finish rendering method, and in this method we just need to do the exact opposite to what we had in the prepare method. So we set the depth mask to true, we disable alpha blending, and we unbind the VAO, and of course we need to remember to stop the shader program. So we now have a fully working rendering system for the particles, but what we need now is a class that can keep track of all the particles in the scene and keep them all updated. And for that I'm going to create a class called ParticleMaster. So this class is going to have a list of all of the particles that are currently in the scene, and then it's going to keep all of these particles updated. Every frame it's going to iterate through that list, updating all the particles, removing any particles that are no longer alive, and it's also going to send these particles off to be rendered. So we need to have a particle renderer in this class as well. I'm just going to create an init method here which is going to initialize the renderer, and this needs to take in the loader and the projection matrix so that we can initialize the particle renderer by calling the particle renderer constructor here and putting in the loader and the projection matrix. Next I'm going to create an update method which will be called once every frame, and the aim of this method is to go through all of the particles in the scene and update every single one of them. And to do this I'm going to use an iterator, which I don't use often, but we need to use it in this case so that we can remove the dead particles from the list while we're iterating through it. So we're just going to iterate through the list using the iterator, so while there are still more particles to iterate, we're going to get the next particle by calling iterator.next, and we're then going to update each particle, and the update method for the particle, if you remember, returns a boolean indicating whether the particle is still alive or not, and if the particle isn't still alive then it should be removed from the scene. So we can do that by calling iterator.remove. The next method that I'm going to create is a method to render all of the particles in the scene, and this needs to take in the camera, and this is a very simple method, and all it needs to do is to call the render method in the particle renderer. Finally, we need a cleanup method to clean up the particle renderer, and again just a very simple method here calling the cleanup method, and we need one more method to allow us to add particles to the scene, or into the list of particles in the particle render in the particle master. So this add method takes in a particle which we want to add to the scene, and it gets added into the list of all the particles. and we're going to call this method from the particle constructor. So in the particle class, if we go up to the constructor here, whenever a particle is created now, it will automatically be added into that list in the particle master. So let's now go into the main game loop and set up the particle master. So the first thing we need to do is to call the init method, and this needs to happen after you've created the master renderer, because you need to be able to get the projection matrix from the master renderer. Then when the game closes, we of course need to clean up the particle master by calling particlemaster.cleanup, and then every single frame, so inside the while loop, we need to update all of the particles every frame. So sometime before the rendering, you need to call particlemaster.update, and then we need to render all of the particles after we've rendered all of the 3D stuff in the scene, but before we render the 2D GUIs and text. So make sure that you put it in that position. It has to be after the 3D stuff and before the 2D stuff, and you'll see why that is next time. So I'm just going to do a quick test here now to make sure that everything's working so far, and what I'm going to do is to check if the Y key is pressed, and if it is, I'm going to emit a particle every frame. So if the Y key is down, then I create a new particle at the player's position, and I need to make this into a new vector3f, otherwise it will use the exact same instance that the player uses, which would cause some problems. I'm going to set the velocity of the particles to be upwards and have a magnitude of 30. They're all going to be affected by gravity. They are going to live for 4 seconds. They're not going to have any rotation, and they're going to have a scale value of 1. So if I go ahead and run that now, whenever I press the Y key, there should be some particles emitted from the player's position, and you can see here that that is working as expected. And of course, if I hold down the Y key, it creates a new particle every frame, so you get a nice stream of particles coming out from the player. So if that's all working for you, then you can delete that bit of test code, and we now have a fully working particle rendering system, and any particles that we create are updated and moved around the world in the way that we want. All we need now is an easy and useful way to create loads of particles, and for this we're going to create a particle system class. Particle systems are basically just going to be things that continually emit particles in a certain way, and I've actually made a simple example of a particle system here to give you an idea of how they could work. So you can download this from the description and have a look at it and try it out, and then you could try to create your own, or you can use the more complex particle system that I've also provided in the description. So this simple particle system here has 4 variables that you can choose, and they are the number of particles that get emitted per second, the particles per second value, the speed that the particles are emitted at, the amount that gravity affects the particles, and how long the particles stay alive for. The generate particles method should be called once every frame, and it takes in the 3D point in the world where the particles should be emitted from. It then calculates the number of particles that should be emitted this frame based on the particles per second value, and it calls the emit particle method once for every particle that needs to be created. And as you can see, the emit particle method simply emits a particle in a fairly random direction using the speed, life length, and gravity settings from the particle system. So in the main game loop, I can now create a new particle system, and I want this to emit 50 particles per second. I want the speed to be 25. I want the particles to only partially be affected by gravity, and the particles are all going to live for 4 seconds. Then every frame I need to get the system to emit particles at the player's position, and then I can go ahead and run this, and you should be able to see that lots of particles are now being emitted from wherever the player is, like this. So you can have a go at making your own particle system class with some more complex settings, or if you want, you can use this one that I created today, and you can download this from the description, and this has a few more options to do with randomizing the particles a bit. In the main game loop, I've set up one of these more complex systems here, and you can see that the constructor now also takes in an average scale value for the particles. I can also choose a direction for the particles to be emitted in, and I can set some error values for the speed, scale, and life length values of the particles, and the higher these errors are, the more randomized the values are. So for example, you can see that the particle sizes are rather varied here in this system because I chose quite a high error value. You can also use the same particle system in multiple locations in the world if you want to, And to do this, you simply have to call the generate particles method again with the relevant position, and then in the game you can see that you now have the same particle system being emitted in 2 different locations. So that is it for this week. Next time we're going to be texturing and animating our particles, and that video will be out in 2 weeks' time. If you'd like to help support the tutorials, then you can check out my Patreon page, a link to which is in the description below, and you can get in touch with me via any of my social media pages. But yeah, thank you guys very much for watching this video. Do subscribe if you haven't already. Have a fantastic week, and I will see you all next time.